Welcome back to the channel if you've been here before in the previous videos, and welcome to the channel if this is your first video here on this channel. So today's video will be a update on what has been happening and going on with the inverter and battery that I purchased late January, early February of this year until now. And it's been about 9 months since then. I have been using it. I completed this install around late March, early April of this year as well, and I've been having the inverter on each day, every hour, every minute, along with the problematic battery that I currently still have. I'm basically going to do a system overview of how I connected all the wiring, what operating mode I'm using the inverter in, and what my intended purpose of building this system was. I am first going to start by taking the cover panel off the breaker box on the left, and we'll go from there. Alright, so I've gone ahead and taken off the cover panel for the breaker box on the left, and I've also moved some of the ceiling panels up and out of the way, so that way we can get a better view of some of the wires. So pretty much the way the inverter is connected between the two panels is I put this inverter as a grid down operating mode, so that's where the AC input to the inverter comes through the three wires on this side over here. They come up and over to the first panel. You can see the larger three wires, the larger 6 gauge and the 4 gauge, black, white, and green. Those wires go up and over, and they come over to the AC input of the inverter. And then of course the output of the AC inverter goes to all these 120 volt single pole breakers. They power all the 120 volt loads. This would be the wire that connects the output of the inverter to those breakers. So basically, if the AC input were to disconnect, whether it's from a power going out or if I manually switch off the breaker to the inverter, it will automatically just pick up and switch over to using the battery as a backup power. I do run the inverter in the UPS mode. I believe that is program option number 3 in the settings. There's 2 options for appliance and UPS, so there's no problems with switching over to things that have like a computer chip or a CPU in it, like a desktop computer, a TV, a monitor, the Wi-Fi router. All those things switch over just fine. I should talk a little bit about how the wiring was originally set up prior to making all the changes. I have my main service wires coming in from the street outside, pass through the power meter, and it's these 3 wires right here, or rather the 2 wires, line 1 and line 2. Between the two, of course, it's 240 volts, and then those cables up there that are pinned on the 2x6 rafter, they used to go directly through the top of this box, and they're held in place, and then they would connect into individual breakers. Instead of those wires coming into this panel, I've had them extended with some of these extension connectors. These type they're similar to the Wago style connectors. You can remove them. You can lift up this orange tab, and then you can pull out the individual wires. So those connectors are UL listed. I do believe code also requires these wires to be pinned or mechanically secured. So I cannot pull on those wires, and they're held in place. So my only option was to extend them to connect to these breakers. If I ever do get a second inverter where I can run the 240 volt split phase for all the 240 volt loads, if I do decide on doing that, I will put the second inverter on just about right here next to the original panel. So that way, I'm thinking this kind of layout would be the most efficient use of the space in this part of the house along these 2 walls. The other option was to have both of these inverters right here on this wall next to each other, and then this single load center panel would probably be closer to the middle of this wall, or maybe I could just have it exactly where it is right now. That's probably something further down the road. Most of my critical important loads are actually 120 volts. With this system, I could basically use any 120 volt appliance in the event of a power outage or when grid power is down. The battery here is still the same battery that is problematic with the bad BMS. I've only cycled this so far about 15 or so times, so not that many cycles on this battery. Typically, for the most part, the loads I have that are always active or can be active at any given point in time, the total combined wattage is typically around 350 on the low end to about 500 on the higher end. 3 compressors, a bunch of computers that I always keep on, a bunch of NVRs, cameras I have around the house. All that combined together can vary between 350 to 500 watts because the 3 compressors can switch on whenever they want as needed depending on temperature. I do have one of the old fridges on a timer. It is the less efficient one. It's not one that I use all the time, but sometimes I have it as a overflow storage for some extra stuff. And when that compressor runs, it's doing 160 watts of load, continuous load. So if you run that for a full hour, it would be 0.16 kilowatt hours. So that's the one I set on a timer. If I don't have to use it all the time, then I could just unplug it. There are other loads that do switch on from time to time. So my gas furnace, both of those motors are 120. So obviously, as long as you have proper gas supply, you can run your heating system during the winter time. So that's very nice. I could still run an air fryer. That's no issues. I can run the toaster oven. No issues, right? I can make a coffee when the power's out. That's very nice. Just a single 5 kilowatt hour battery for me really isn't enough. It would be more ideal if I had at least one more battery for 10 kilowatt hours. That is probably something for the future. If I ever do decide on another battery or another inverter, I will also make a future update video on that as well. I want to talk about charging the battery in the event that I don't have grid power. So let's say grid power is down because I had some really bad weather come in. If there was a bad storm that happened in my area and my local substation transformer was knocked out, for me in this area that was about 3 years ago, I was out of power for a full week. And at that time, I didn't have the battery in the inverter 3 years ago. So that wasn't very convenient. But if that ever were to happen again, in that case, I actually do have a portable generator recharging circuit set up. I hooked up a generator lockout switch where if your primary switch from your service wires coming in, if it's on, your generator circuit breaker has to be off. If your primary big breaker is off, then you can turn on your generator charging circuit, right? So the 2 switches here, only one of them can be on at the same time. So it never allows both, and that's what the lockout plate does. This breaker right here is a 30 amp breaker. This is a outdoor UFB wire. The lockout plate is actually right here. See, that's set in place in this position between these 2 breakers. My inverter generator does 30 amps with the TT30P RV receptacle, 3,000 watts on propane running watts, and then the gasoline running watts is 3,200. And I could use the generator directly as an AC input for any active load that is on this panel right here. And then of course, if the battery was not at a full state of charge, the inverter would also use some of that wattage or some of that power from the inverter and start charging the battery as well. I can set the charge rate in the inverter settings to 50 amps at the battery voltage, 2,500 watts of power going to the battery. The battery charger in this inverter here, peak efficiency is around 88%. So for any given wattage of AC input when you're charging a battery, 88% of that power will be converted back to DC at the battery voltage and used for charging. So the charge time for a single 5 kilowatt hour battery here. I find it to be 2 hours with propane and then around 1 hour 45 minutes with gasoline. So it's not too bad. If I do add more batteries, it's going to start taking a while. I would also be charging at 120 volts. If I do have a second inverter at some point in the future for 240 volt loads, I would probably upgrade my generator to a 240 volt output as well. So that way I can use both inverters to charge for faster charging, right? Otherwise, I can only use one of the two inverters for battery charging. Let's see what else I haven't mentioned. I do not have solar panels with the system. I'm not likely to have solar panels with the system anytime soon, to be honest. I've done some calculations on the return on investment for based on how much kilowatt hours worth of energy I use per month, the rate that I'm currently paying, and of course the amount of sunlight that I have in my exact area, and the numbers don't look too good. I'm seeing like at least a 6+ year return on investment. For any significant size solar array, that gives me enough wattage to run, say, electric clothes dryer, right, which is a 5 kilowatt load. I figured that kind of return on investment is rather long. And so I suppose the next best option is to probably do a grid down battery backup system with a standby inverter. Most of the time, this inverter is really just idling. The inverter circuitry is on. It's like if you have the inverter in battery mode and you don't have a load connected to it, and you check how many watts of power drawing from the battery when idling, the MPP Solar LV6548 will draw around 60 to 65 watts. And I do believe that is the case here for my operating mode. I do set it on utility solar battery. It doesn't really matter. In the event that grid power goes down, it would just switch over to battery anyway because there is no solar present here. I'm currently paying about 21 cents a kilowatt hour, which probably seems quite high, but that 21 cents a kilowatt hour, the total price of that includes a service charge and also a supply charge, a delivery charge and a supply charge. So supply charge is like around 10 cents a kilowatt hour, and then the other delivery charge is 11 cents a kilowatt hour. So it adds up to basically around 21 cents a kilowatt hour. It could drop down to 19 cents a kilowatt hour from time to time, but the past 3 years for me, it has consistently been 20 or 21 cents a kilowatt hour. You know, I use anywhere between 400 kilowatt hours on the low end to 750 on the very high end. But I suppose a long-term average for me is probably around 550 kilowatt hours per month. If you look at a 12-month average, around 500 to 550. I don't have enough sunlight to decrease the return on investment because I got a bunch of trees out in the surrounding area that are really tall, and it's actually twice the height of the house. So I got one in my own backyard that I could cut down, but most of the other trees are actually not in my backyard. They're in the neighbor's backyard. And so I talked with the neighbors about if they wanted to trim down or a few of those trees just so I can get just enough sunlight on the roof of the house for the solar panels. But I would say in the summertime around late afternoon hours, I am basically in the shade. The roof of the house is not in direct sunlight during the summertime. Like around 4 to 7 in the afternoon, we don't have any sunlight over the roof of the house. So there's just not enough consistent sunlight throughout the day to make use of a solar system. There is some sunlight during the early morning hours, but that's probably not enough to get a shorter return on investment. So the next best option was to do something like this. Since I've installed this system, I have yet to have one power outage or a power disconnect event that would cause my computer to shut off or restart. You know, even if it's like an intermittent power drop where the voltage falls out of spec, that's called a brownout. Just one power outage event or just one brownout or blackout is enough for me to say this system was worth installing as a next best option if you don't want to use solar because you don't have enough sunlight. Paid $3,000 for the battery and the inverter. That includes shipping with a bunch of extra stuff, the wiring, the new breaker box. I did not have to replace those breaker switches because this new panel right here uses the same set of breakers as the original panel. I did not buy new breakers. I took these 120 volt breakers and I just move them over because if you buy a new breaker panel made by the same manufacturer as your old panel, then your breakers are compatible, right? You don't have to buy a new set of breakers if you really don't have to, right? So that's basically what I did. I buy the least amount of wiring possible for this system. this white wire here is actually a 6-gauge wire. I did not have 4-gauge available at the time. For the neutral wire, the black hot wire here, both of these are 4-gauge. That's fine. That's not a big deal because the BMS in this battery is underperforming, under spec. So I am not able to use the full 6.5 kilowatt hours output from this inverter anyway. The neutral wire at 6-gauge is perfectly okay. If I do plan on changing batteries or adding more batteries, I will change that 6-gauge neutral wire to 4-gauge to match the black hot wire. Every video that talks about this particular battery has said good things about it. Every single video review of this battery that you'll find on YouTube, whether if it's paid or not, sponsored or not, everybody has said good things about this battery. Everybody says this battery works to spec. But I just happen to be that one unfortunate person that gets a bad BMS, right? I still haven't really fully decided what I want to do with it. I was thinking about getting rid of it or selling it secondhand, or maybe just leaving it the way it is with the bad BMS and just calling it a day. I know I did show this in previous videos. If you thought the BMS in this battery was not programmed correctly, where the reason why I was not getting 100 amps of output current was because the BMS software had a programming error, that's actually not true. I will show you in a moment where serial comm connection cable. The BMS is programmed correctly to allow discharge at 100 amps, but it just won't do it. I will open the SOK tools, BMS status monitoring, right? So if you'll click over here to parameter settings, this is the tab where you can see what the BMS is programmed to. So let's check read all, and we can see allowed discharge current for the BMS is programmed for. So I didn't show this page the first time around in the first earlier videos when I demonstrated the BMS problem. It does appear to be programmed correctly, but just won't allow it. I don't have the ability to modify any of these settings because it is firmware locked. Also, these stickers on the inverter, yeah, I put these stickers on. Say what you want, I don't give a damn. I will probably change these stickers out at some point to some other kind of stickers, something a little different. Let's see what else I want to mention. This board right here, I want to talk about this right here. This is how I use the inverter for the past almost 1 year now, since I completed this project. If you're familiar with the LV6540 inverter, having this box attached to the the front side of the metal frame or the casement of this inverter, I find that it actually significantly reduces the airflow for the fans. It's building up a lot of hot air in this area because having this metal case covering the front side of this area, it traps all the heat in, and it will make the internal temperatures of the inverter a little bit hotter. So what I decided to do was, if you were to take this cover plate off, what you'll find is, of course, there would be another back plate. Okay, this back plate would normally be attached to the inverter through the 3 mounting screws here, here, and here. They are attached to the 3 screws up here. The circuit board was attached onto these 4 screws on this side. I pulled out these 3 wires from this cutout here that was part of the front metal case, and then afterwards I had to find a way to re-secure this board in place somehow. And so what I did was I cut a piece of PVC plastic. I made a hole through the panel, this area here, and then of course I used one of the original screws to attach this plastic panel in place as a location for this board to install. This board would normally be rotated 90 degrees. I just turned it over sideways. I think this is better. It allows for more airflow. I don't find the noise too big of an issue. It's not too loud because I'm not in this part of the house all that much. It is a smaller area here. The space is a little bit more confined. The air is drawn in from this top of the filter box right here. I did add an extra microfiber lint-free mesh. It acts like a cloth on top of the original filter to add some extra filtration, and it's just to try and minimize the amount of dust buildup that I get. There's one on each side. I've always used it like that as well. I do find it does help reduce the amount of dust buildup that catches inside. Usually it likes to stick in the areas that don't have proper airflow. So, for example, in the very corner of the inverters, down on the very edges, those areas tend to build up more dust and just general debris. The fan blades also catch a lot of it. So I do take the cover off and I clean that out with a air compressor that is powered by another portable power station. That's a separate all-in-one unit. I disconnect power to the inverter. I switch it off because I don't want to be, touching electrical stuff with the cover open, and messing around in there. So just rather be safer and not damage my equipment. And I use that compressed air to blow out any additional dust along with a brush to sweep it as well. I do that once every 3 months. I find it's better to clean it a little more often consistently, not try to clean it when it's really, really dirty. So that's pretty much a wrap-up overview of this entire system. Really, I've had no issues with it. Everything works pretty darn well with this inverter. Most of the appliances that I use don't have a problem. The inverter sine wave, when it's running in battery mode. I know some other content creators in the DIY solar space mentioned that they have problems with flickering with some of these high frequency inverters. And I do want to say that I actually have had that issue myself with LED lights. I've got various different LED lights around the house. There's only one brand that I happen to have an issue with. If you're curious which brand of LED lights that is, it is this one right here. So nothing against this brand, but I am just saying that my experience with EcoSmart LED light bulbs, I purchased these from Home Depot. I got these from there, EcoSmart. These are 100 watt equivalents. I also have these in 60 watt equivalents. And when I use this inverter in battery mode, these LED lights will have like a really bad flicker or strobing effect. I do have another type that is the chandelier style. I don't know what the socket number is called for those, but those like skinny ones with the much smaller lamp base, made by the same brand, they also flicker as well. So it's that really bad strobing. Those were 25 watt equivalent. It's the only brand of LED light that I've had this strobing issues with. I've used other light bulb brands and none of them have issues with this. The Sylvanias don't have issues. The Philips don't have issues. The GEs don't have issues. The Osrams don't have issues. The Panasonic has no issues. It is only this particular brand that has that kind of problem. My guess is probably something with it's something to do with filtering. So that's basically a wrap up for this system.